is Stefanie Elgeti. I'm one of the organizers of this course. And I'm welcoming you not only in my name, but also in the name of Matthias Möller, who's my co-organizer, also in the name of Gianluigi Rozza, who's one of the lecturers who's already present here in the room, and also in particular in the name of Antonio De Simone, who's the Secretary General of CHISM. Let me say a few words about CHISM. I don't know, maybe it's the first time that you're here. So CHISM is the International Center for the Mechanical Sciences, and it was founded in 1968 when people were trying to look for a place where we can exchange ideas about mechanics, and there were several locations in the running, but in the end, it was Udine because of this beautiful palazzo here, because of the city of Udine that is in the center of Europe. It's small enough so that there's not too many tourists here that distract people, but it's a very historically interesting city. It's a very beautiful city. So I'm very glad that we were given the opportunity to organize this workshop here. CHISM is a nonprofit organization with the aim of advancing knowledge in the mechanical sciences, and one of the core business of CHISM is to organize these courses to really bring the state of the art in mechanics to people. It is funded by the city of Udine, by the province of Udine, and also by the Friuli Venezia Giulia region. And yeah, I'm very glad that we have the opportunity to be here the whole week and to hold this course. I would like to thank the lecturers for taking the time to come here and to teach. I would like to thank the CHISM Scientific Council for selecting us for this course, because it's not everyone is selected to be able to hold a course here. I would like to thank ECOMAS for endorsing this course, and then of course in particular the staff of CHISM, who is really helping to make this a successful event here with their local organization, and whom you've already met during registration. Well, what can you expect from the next week? So, okay, that was with quite some delay. All right. Let me introduce the speakers to you. So, Matthias Möller from the Technical University of Delft will speak on physics-informed neural networks, in particular in the context of isogeometric analysis, and he will introduce also something called IGANET, so like a combination of the two. I will speak today about, and I will give you the introduction to the week. So I will introduce engineering design concepts in the classical sense to make sure that you know how people are doing it right now. I will also give an introduction to neural networks, so that then you're prepared for the lectures to come where these concepts are then used together. Then we have Sebastian Schips from the Technical University of Darmstadt, who will speak on robust design. So how can uncertainties be incorporated into the design process? There's Gianluigi Rozza from CISA, who will speak on model order reduction and how scientific machine learning can help us in model order reduction, and then in the process in designing new components. There's Paris Pentikaris from the University of Pennsylvania, who, well, takes a very long trip to come and join us here to speak about deep O-nets, neural operators, and their applications in scientific computing. And then last not but least, there's Eli Hashem from Amin Paritech, who will speak on reinforcement learning and the use of reinforcement learning in design optimization. So this is the week, and it will look as follows in terms of schedule. So we already had the registration here on Sunday morning. We're now in the first lecture, so introduction by myself will be today. Then highlighted in red, we had to trade a little bit, so a last minute change in the program. So this afternoon you will hear me instead of Gianluigi, and then tomorrow you will hear Gianluigi again. He's sorry, but there's no reason to be sorry. I think we will be just fine. Yeah, so this is the schedule. Here we have coffee breaks. There's a coffee machine where you can get coffee. Next to the registration, you go up the stairs. So there's a machine. I hope that it works. They said that it will be refilled regularly because we're a lot of people. But yeah, I hope that this works out. There's also a lunch. You already received instructions regarding the lunch, I suppose. So you have vouchers for a buffet lunch. We will all go to the same restaurant. So either we all get lost or we all make it, I guess. And also this evening, there's a welcome aperitif here in the courtyard. What else? There's restrooms in the back of the room and also another restroom under the stairs in the main hall. Yeah, I think that's all we need to know for now. And we can get started. So this is supposed to be an interactive thing. So please feel free to make it interactive and interrupt us at any time if you have questions, if you have comments. You can share your own experiences. So please feel free. I don't want to talk at you all day. So I would like to talk with you. That would be great. Absolutely, yes. Let's start with the introduction to engineering design. So about myself, I'm a mechanical engineer by training. I studied at RWTH Aachen University, and actually I originally specialized in production engineering, or I became interested in simulation. And right now I'm professor for lightweight design at Technical University of Vienna, and also still part-time at the Chair for Computational Analysis of Technical Systems at RWTH Aachen University. And my research interests are numerical design, optimization, finite element simulations, so isogeometric analysis, and machine learning. So just so you know a little bit about my background. And I will tell you about the engineering design process in general, how nowadays it really does not look like this anymore, where people work on a drawing board, but many things have changed, many things have become more complicated. In particular, then, we will speak about methods for shape representation, because if you want to find a new design, a new shape for your component, you need to be able to represent this somehow in a computer in order to use. They should already be uploaded. Okay. So for the online participants, the question was whether the slides will be uploaded. They should be available to you in the internal area, CHISM. And then, most importantly, we will speak about methods of automatic form finding. So in our first lecture, this is really a bit confusing for me. I switched slides what feels like a minute ago. I can go back. But I cannot now. If every switching of the slide takes that long, we're going to be here all night. Cool. In the first lecture, I would like to answer the questions, what are actually tasks of a design engineer? So this will be, and it's Monday morning, so it'll be a slow start. I will have some pictures and videos, and then I will give you an overview over shape design and what are the questions that we need to answer there. Wonder why that is so. Now I'm regretting that I have so many slides. Yeah. The slides have not been uploaded yet. Okay, but they should be. So I sent them, but and I need to confess I sent them very last minute. Never happens to you, right? So I hope that they will be available very soon, but definitely they will be available. Why did I become interested in engineering design? I'm very much afraid of heights, and then it used to be that when I needed to walk on such a structure or something, I would always tell myself, don't worry, someone computed this. And now I know who computes these things, and it's not a consolation anymore at all. So what are our problems? Let me start with a quote by Christopher Alexander. So he says, we're never capable of stating a design problem except in the terms of the errors we have observed in past solutions to past problems. So we will learn more from failures than we will learn from successful designs. That's the idea. And this is where we will start to look at some design failures. So essentially, wait for it. There's going to be a funny picture. So much suspense. I wonder why that is. Why is it my internet connection maybe that makes it so slow? Or well, I already see it here. It's just Teams that's not processing it somehow. Yeah, that's what worked last time. Yeah, probably. It is. Okay, so we will talk about these moments. There was so much suspense in that picture in that respect. Let me go through all of the overlays immediately. So there's several categories of design tasks. So the highest discipline, of course, is to come up with a completely novel design. This is not the general design task. In fact, most designs are adaptation designs. So we already have a car and we try to make a different car out of it, or even more design of variants. So you have a whole collection of similar products that then come in different sizes, different colors, whatever. So these are the design tasks that we have in general. And then if we look at the levels of detail in design, then the top level will be the system design. So the whole rocket, the whole car, whatever it is. And on the conceptual design level, we then try to think about how the individual components of the system, how they interact. How do we transmit forces? How do we keep the components together? Do we use glue? Do we use screws? So these are conceptual decisions. And then we come down to the individual components, where maybe we can select from catalogs, or we design individual components. And this is what we will be talking about today, or in this week, basically how to design individualized components and how numerical methods can help us here. If we look at the design principles and how we can avoid errors, then let me give you another quote. So conceptual errors are invariably human errors because a conceptual design comes only out of the uniquely human creative act of transforming some private concept from the designer's mind to some public concept can be described to and modified by other humans. So the question that we can look at this week, is this still true? Or can this creative act that was attributed to the humans here, can this be transferred to artificial intelligence somehow, maybe? But in any case, for now, there's these general rules that are advised if you like to try out a new design. And there's some examples where it went wrong. So around 450 BC, there was this task of moving a pedestal for a statue for Apollo from the ferry where the stone was broken to a temple on Sicily. And how people did it at the time is that they used wagons because they're easy to maneuver, but with such a heavy load, they get stuck in soft ground with the wheels. So people started to think of different options. So if you have tried to, I already switched slide, I will try to introduce you to it. So these columns are circular. Also the wheels are circular. So you could try to use the column as a wheel. There it is. Now it disappeared again. Okay. So we use the column as a wheel. It's still easy to maneuver. It's now manageable on soft ground. However, we're restricted to circular columns, and we need the pivot cups here that we need to cut into the column. If we place the column like this, where it's covered at the top and the bottom, it doesn't really matter. But for the statue, maybe it does matter. So Metagonus came up with this idea where the column was inserted into these big wheels. So now we also have arbitrary shaped columns, but we still have these pivot cups. And now comes the failure in a sense. So Paconius decided to put this pedestal into big wheel. Then he wrapped this rope around and he had these oxen pull it. So this is very hard to maneuver because you cannot move around somehow. And also you have to restart it over and over because you have to recoil the rope. So if he had only made the prototype, that would have already helped a lot. And it's very, at least nowadays, it's very easy to make a prototype because if you just take a roll of yarn, it's exactly that. And if you try to pull it, it's not gonna be very straight, the motion. So what else? Maybe you've seen this video before. So the Tacoma Narrows Suspension Bridge, which at the time had a total length of 1.8 kilometers and the longest span of 0.85 kilometers. The sound is not important in case you can hear it. And it failed catastrophically. Hard to believe that this can even happen, that the whole bridge can oscillate like that. And this was because of wind-induced oscillations, only 7 months after it has been opened to the public. And what happened? So people took previous bridge designs and just scaled them up without taking account for the underlying design principles. So, and on top of that, the large number of successful designs that they had had before led them to reduce the safety factor. This made it even worse. So we learned from that seemingly sound concepts for improving on familiar ways of doing things continue to hold surprises. So we need to continue to challenge our own designs and also let others challenge it. Another example. So this is the de Havilland Comet, an airplane. And in 1954, two of these airplanes disintegrated mid-flight for, at the time, no apparent reason. And actually 56 people died in this incident. And the reason why this happened is that they decided to put these almost square windows into airplane. And almost square windows are basically hey, back and forth. Okay, almost square windows are basically like your Kit Kat bar that cracks because you have a stress concentration in the corner. And in theory, this should have been known to people. So if we compare the stress flow lines in such a scenario or with the radius, then here we get the stress concentration that here we do not have. And in any design class in mechanical engineering, you learn about these geometry factors that give you an idea or an estimate of the stress concentration or the average stress for given geometries. And as you can see here, you always have the radius. You are never supposed to have these 90-degree angles. And as I mentioned to you, I'm also working part-time at RWTH Aachen University, and there's a relatively new building that was constructed there with a 90-degree angle. And I always ask myself, why? Okay, so sometimes design changes are really motivated by aesthetic or economical reasons. So do not let yourself be fooled by this. Okay, last example, Hyatt Regency Hotel in Kansas City. So people try to build these aerial walkways. They're suspended from the ceiling. So you can see the rods from which the walkways are hanging. And this is an illustration of the original design. That went too far. So this is the original design. You have this long rod and you have each platform here is held by one nut with respect to this rod. And then someone had the idea, we need to change that. The rod is too long. We need shorter rods. So they changed it as follows. I don't know, you want to get a coffee or something. Okay. So they changed it as follows. So almost looks the same, except this was the version before. And now this nut has to hold twice the weight than in the original concept. And that's what happened. I can already see what happened. That's the final result of this design change. So, do the math. How can we do the math? That's our question. That would be our question this week. So, in order to avoid this, in order to avoid all of these things that we saw here, the design process is extremely structured. And let me give you an overview of what those steps are. So we start with a precise definition of the task. So we need to record customer wishes somehow. And the interesting part is we need to record the spoken and the unspoken customer wishes. There's going to be a market analysis of what is already there. And of course, we're in a framework of norms and regulations that give us some idea in which direction we need to go. Then we define the functionality structure and the solution principles. So this is what I said before. How do we transmit forces? How do we bring the components together so that they stay together? And only then comes the actual product design, which is where then the numerical design part becomes important. So in the product design, maybe we have experience with similar products, and this gives us a starting point. There's the catalog components that I already mentioned, and otherwise there's certain design methodologies in the sense of creative techniques on how to come up with new designs. Then after the design, there's a step of testing and assessment. So there's where the prototypes come in, where numerical analysis comes in, where experiments come in, and where we really need to challenge our product design. And then finally, there's a step of product optimization. Yeah. So this is the workflow for a successful and safe design. But what does safety even mean? I mean, there's many ways in which a design has to be safe. So a technical component is considered safe if it fulfills its purpose reliably and if it is of no danger to people and the environment. So these are two aspects. So the component itself is not supposed to fail, but also even if it's working properly, it can still endanger people. And this is something that one needs to consider. So this German industrial norm defines safety as a situation where the risk is lower than a limit risk. So the risk here is defined via the probability or the frequency and the extent of damage. And the limit risk is the largest still acceptable risk with of a specific technical process or state. But this can be very hard to quantify what is an acceptable risk. Let me go through all of the steps immediately. So as I mentioned, there's many aspects to safety. We have the component reliability, functional reliability, operational safety, workplace safety, environmental safety. So there's many aspects that one needs to consider. And if we look at the numerical design, you will see that we're sort of restricted in our view. They're still very, very much restricted. Just as a brief idea, so there's two principles towards safety. There's the direct safety measures and indirect safety measures. Direct safety measures are, for example, the safe life method, in the sense that I designed the component in such a way that it will last the desired lifespan very most likely. Whereas, for example, the fail-safe method, there I allow for the possibility that this component fails, but if it does it in a safe way. It doesn't break the entire system. And there's redundancy. Indirect safety measures can be like the machine, a robot, for example, that's in a cage. That would be an indirect safety measure. This is reliable, it's very effective, and it has to be non-circumventable. And well, finally, just a brief glimpse of what are functional principles and how can they be employed. So embodiment design principles are, for example, the principle of force transmission, which is a very recurring task in engineering. So here we aim for short distances and closed circuits. So if I want to transmit a force, I want to have a short distance. I don't want to go around, or at least I want to have a closed circuit. And a principle of division of tasks. Every component should be responsible for a simple and a unique functionality. And this makes the system design much easier. Okay, so this was a general overview over what are some challenges for general engineering design. Now we will really zoom on design of individual components and how we can do so using design optimization methods. So let me give you first an overview over the broad concept of shape design, and then there will be more details in the coming lectures. Where do we need methods of shape design? Everywhere, basically. In architecture, so this is a building in Qatar where there's been a topology optimization, apparently, of these columns. Very early shape optimization was used in aerospace engineering for airfoils. In structural mechanics, of course, where we can, or in particular, lightweight design, where we make the components as light as possible, and they still, of course, need to fulfill their functionality. Also in fluid mechanics, like this artificial heart here, or this heart pump. So there's many applications, and I guess you're here because you're dealing with one of these applications, very most likely. What is the challenge in shape optimization? I think it's so easy to explain that you can even explain it to a child. So I borrowed some Lego from my son to explain it. Hope that this video is running. So the idea is here, we build a bridge. We already have the two columns, and we build a paper bridge that holds this cow. Obviously, like this, it doesn't work. So we need to change the shape of the paper. We perform a shape optimization. So for example, we can fold it and we can introduce some creases, and this will increase the stiffness. And then, in fact, it does hold the cow. This is not the only solution. We can increase the stiffness in many other ways. So there's another example here, which now is a design that is actually able to hold the cow, but it cannot walk on it anymore. It can just sleep on the bridge, unfortunately. But it's stiff enough. So this is one key message in shape optimization. There's many solutions, and we need to deal with this somehow. And in fact, even if you really don't know what to do, and you just crumple up your piece of paper, even then it works. Yes, please.
Sorry, is this because it's like an inverse problem? So it's in the side?
Can you repeat the question?
If the reason for the software application is that maybe something like an inverse problem, so they are usually ill-defined.
Yes. So the question was, well, I'm sorry, I'll repeat for the online community here. So the question was whether the reason why there's many solutions is that it's an inverse problem and they're often ill-defined. And I guess we can start to argue about cause and effect. The inverse problem is ill-defined because there's many solutions, or the other way around. In any case, I guess sort of intuitive that there's not only one way to build a bridge. There are many ways. And so here's the summary of the problem. And by the way, if then we decide we want to make it later, we can also cut some holes into our structure, and this would then be a topology optimization as opposed to a shape optimization. The first and maybe even most important step towards finding optimum, from my point of view, is the definition of the objective function, because there's so many things that can go wrong when you define the objective function. So without a quantifiable goal, there's not going to be an optimization. And sometimes we're a bit lax when we look at objective functions. So we find something that we think will work, and we just use it directly in the optimization. But this is not advisable, because so I put this phrase here, can't you please tell me where I want to go? Is we have this idea, we want to do something better, we want to optimize this, but we don't really take the time to think about optimize with respect to what? And even if we know, so there's many energy, cost, weight, and there's so many options on how we can optimize. And even if we do know, then what is the best way of describing this in an objective function? I mean, we want to find a function that puts all of our optimization desires into one number. This is very difficult. So my advice would be not to just take the first objective function that you can think of, but to use several and then to challenge your objective function outside of an optimization procedure. So you take certain outcomes that you can think of, and then you try your objective functions, how they behave. And I have a slide about this in a moment. So the objective function is a measure for the performance of the underlying system. Sometimes people also say quantity of interest or loss function, depending on the scenario. So I will use objective function. I will use the letter J. And we're thinking about shape optimization. So this objective function depends on the current shape configuration, which I will denote as omega. And omega comes from a set of admissible shapes. And then we can have some constraints on this. So definitely we will have some equality constraint, and we could also have some inequality constraints on our objective function. So with respect to our example, and again, let me go through all the overlays. So the domain omega, this was our paper. And we were able to change the shape of the paper. And the set of admissible shapes contains all shapes that we allow in principle. So here, for the bridge as objective function, we could use something like the maximal deflection under a certain load. So how, for example, we can use the compliance, which is, so in case you're not familiar, the compliance is the inverse property of the stiffness. But we always want to minimize, which is why we minimize compliance instead of maximizing stiffness. And here in our case, the equality constraint is usually a constraint based on a PDE, because we want to be sure that this system that we have here conforms to some physical law. So it behaves according to certain mechanical laws. This is why we have this equality constraint, usually in shape optimization. So let me give an example of a simple task in terms of objective function. So we want to compute shape deviation between two shapes. Blue would be our desired shape, and black could, for example, be the result of some manufacturing process. And we want to see how much this result deviates from the desired result. So here's 3 examples of how one could try to quantify this, but I'm sure if we brainstorm, we can find many, many more. For example, we can try to compute the area that is not overlapping between these 2 shapes. Since we think about this whole thing being represented in a simulation context, so for example, with finite element meshes, maybe we have conforming meshes and we could compute the distance between corresponding nodes and use that as an objective. Or what is actually used in experiments, you move along the outward normal of your blue shape until you hit the black shape, and then you compute these distances and you sum them up. So there's many options. So how do we know which is the best one? So first of all, I think we should apply the objective function to the full range of possible outcomes and then assess whether our expectations are met. So if we know that in our process, maybe these kind of shapes can actually occur, this was our desired shape, remember? So then we take our objective functions. Now this is artificial, this is not with respect to the actual objective functions. And for each of these shapes, we evaluate the objective function. And since this is the desired shape, and here for the turquoise objective function, we have the lowest value for the circle. Turquoise is already out. But there's still 2 left. So how about we assess the sensitivity of the objective function with respect to our parameter, because that makes it easier for the optimization algorithm to handle it. So maybe we would prefer red over gray. And then also we can take into account computability. But again, let me really stress, try to test outside of your optimization algorithm, because if you put it directly into the optimization algorithm, you will probably not hit all of these shape variants, and you might not even notice that something is going wrong. Okay. So once we have the objective function, our numerical design process is an iterative process. So we start with an initial guess for our shape, which we need to parameterize in some way. And we will talk in the, not the next, but the one after, we will talk about how to parameterize this. So we have certain shape for which we then evaluate the constraint. So this gives us, for a certain shape parameter configuration, gives us the solution of our underlying physical model. So the structural simulation, for example. And using this, we can evaluate our objective function. And this value is then given to an optimization algorithm, which then decides which is the next configuration, shape configuration that we should try. And at some point, we stop, for example, if there's no significant change in the objective function anymore. Okay. So this concludes the first lecture. We spoke about what are the tasks of a design engineer. For example, the definition of functionality structure and solution principles, and of course, product design, testing, and assessment. And now we're going to start to talk about how we can help the design and the testing. And I gave you a short overview over shape design. So we said that the choice of objective function is very important. And to do so, we modify the domain omega and check whether this is still admissible. Okay. So now we will speak about methods of shape representation. First, in general, how can we represent shapes? Then I will introduce you to Z-splines, B-splines, and non-uniform rational B-splines, because we need that both for the shape optimization in order to represent shapes, and then also for the isogeometric analysis and the EGA-nets. So all of you need some background on this. And then I will speak a bit about solution strategies of optimization problems. But now, wait, now it's supposed to be coffee break, right? Ah, sorry. I was so in the flow. I was about to continue. No, so after coffee break, we will talk about this. So thank you very much so far, and I'll see you in half an hour.